Yeah, good afternoon, ladies and gentlemen. Welcome to JCSF physics tutorial class. And we continue this afternoon from where we stopped. So if we could remember, in our last class, we stopped at acceleration under the motion. Today we will start with velocity time graph. So we start with velocity time graph. So let us suppose that an object traveling along a straight path. So let's assume that an object traveling along a straight path has the following. Let me draw a table. Has the following velocity of the first 12 seconds of its motion. Let's assume a body travel in the straight path has the following velocity for the first 12 seconds of its motion. So we have velocity, then we have the time. Time is measured in seconds. Velocity, that is meter per second. Meter per second. So today we are dealing with a velocity time graph. And I said that let us suppose that an object traveling along a straight path has the following velocity for the first 12 seconds of its motion. An object traveling along a straight path that has the velocity, the following velocity for the 4 seconds. So let's say the starting will be 0.0. So when the body is at rest, here now we have 5.0, we have 10.0, we have 50.0, we have 7.5, and finally we have 0.0, because the body will definitely come to rest. So at the rest, before the body starts the journey, so the second is 0. Now we have 2, we have 4, we have 6, we have 8. Zero, 2, 4, 6, 8, and 12. That is an error. Okay. Like a slight error here. Let me redraw the table. Sorry for the subtraction. Let me represent velocity as V so that the ball can contain. So V, meter per second. Now time as T, second. So with this now, I hope the board can take everything. Now, the body at rest, 0.0. Here now will be 5.0, 10.0, 15.0, 15.0, 7.5, and the body will finally come to rest here, 0.0. Now, this time at the beginning of the journey of the object is 0. So 2, 4, 6, 8, 10, 12. Don't forget we are dealing with the time graph. Now, if we plot a graph of velocity against time, if we plot a graph of velocity against time, we obtain a velocity time graph which describes this motion. When we plot a graph of velocity against time, so what we are going to obtain is velocity time graph, which describe the what? So this motion. So we describe this motion. So let's try to look into it. So let's try to look into the example. Now, we are dealing with velocity graph. What is on the table now are going to appear here. So here is the rest 0. Now this is the velocity. Here will be the time. This is the time. Second, and here the velocity, which is meter per second. I hope you are going with me. Now, when display is 0, we can have, when we do it at 2.5, then this place will be 5. We have 7.5. We have 10. We have 12.5. We have 15. Then we can have 17.5. So in the time lane, we have this 0, 2, 4, 6, 8, and the final point. We are plotting the graph of velocity against time. So when we plot it, so we are going to describe the motion of the body inside the graph. Now, when we look into this body now, when you look into it, when the body is at rest, at the beginning, when velocity is at 0.0, the time is still 0.0. This is okay. Velocity, when velocity is 5.0, then the time is 2. 5.0, then the time is 2. The time is 2. So here, now 10.0. When velocity is 10.0, so the second, the time is 4 seconds. The time is 4 seconds. 4 seconds. So if you look into it, how the graph is moving, you get it clearly. When the velocity is 50.0, so the time is 6 seconds. 50.0, the time is 6 seconds. Now, when the velocity is 15 meters per second, the time is 8 seconds. Now, when the velocity is still 15 meters per second, the time is 8. Now, which is here. When the velocity is 7.5 meters per second, 7.5 meters per second, now the time is 10 seconds. 0.5. 7.5. We can get 7.5 here. Then the time is 10. 0.5. Now, ten, 0.5 will be somewhere here. Now, 10 seconds. Drawing out this graph now. We arrive that on the motion, the body gets to some level where it maintains a uniform acceleration. That is when the velocity is 15 meters per second. Now it maintains the object maintains a constant, a uniform velocity when it was 15 meters per second, and it maintained the uniform velocity for 2 seconds. That is from 6 to 8 seconds. Now there is a uniform velocity here. The uniform velocity here. Yeah. I can hear you. Now, so according to the graph, if you look into the table, the velocity at when the object reach the velocity of 15 meters per second, it maintains the same. It maintains a uniform velocity for 2 seconds. That is 15 meters per second for 2 seconds. So that is what happened here. Now, when the body reach the velocity of 50 meters per second, it maintains uniform velocity for 2 seconds. That is when in 6 and 8. If you look, 6 and 8. Now, the table above this, the graph representation of each. Now, a velocity, these are the data to represent the velocity. So when the body is at rest, it is 0.0 velocity. Now, when the body is the object is at 5.0 meter per second velocity, now it accelerates 2 seconds. That is 2 seconds as time. 10 meter per second, 4 seconds. When it reaches 15 meter per second, it maintains a uniform velocity. So in 15 meter per second, from 6 seconds to 8 seconds, before it now starts to come in to rest. And the body, the velocity of the body now 7.5, when the time was 10 seconds. Now the body comes to rest at 12 seconds. And that is what is on the graph here. Now, if you look, this is the starting of the object when the body is at rest. Now, here is when the velocity is at 5.0 meters per second, the time is 2 seconds. Now, when the velocity is at 10 meters per second, now the time is 4 seconds. Now, when the body maintains uniform velocity, that is 6 and 8. Under circumstances now, we can name this point where the body maintains uniform velocity as A and this place B. And here can be P and this place may be Q. So here now we have represented this table, this velocity time graph. So this table as a velocity time graph. Now it was given as table. Sometimes the table may not be given, whereby they just give you that the body moves in a velocity. So, and based on the question, you can draw out the velocity time graph following the table. So this table now, this is the graphical representation of this table of a body. So moving on a traveling along a straight path. So this is the velocity time graph of it. Now let's look something into the graph that is on the board. Now I'll try to label some part of the graph so that we can look into some little calculation on the graph that we just draw at the board. So when the body maintains uniform acceleration, this when it reaches 15 meters per second, AB, we call it AB. Now, PQ, this place can be, we can call this place C. That is, and this place where the body comes to rest as D. When if this place is A and this place is B, this place will be C, and when the body is at rest, will be D. So do not get twisted. When the body maintains uniform velocity at 15 meters per second, so we call it A. When it maintains uniform velocity 15 meters per second at 8 seconds, so we call it B. Now, when the body is trying to go to rest, 7.5 meters per second velocity, 7.5 meters per second, and 10 seconds, we refer to it as C. And when the body is at rest, so we refer to it as D. Now, here is the starting of the object. Now let's look into it. Along the, okay, let me name here O. Let us name here O so that we can get the number parameter of the graph we are dealing with. Now from OA, along OA, if you look at along OA, the velocity increases with equal amount in each second interval for the first 6 seconds. In OA, from OA like this, starting from O to the body reach here. If you observe, you see that the velocity increases with equal amount in each second interval for the first 6 seconds, equal amount. So for the first 6 seconds, so that is 2, 4, 6. So it increases with equal amount for the first 6 seconds. So the uniform acceleration along OA is given. We want to give the uniform acceleration along this place now, uniform acceleration along this place now. We can say velocity change all over time taking for change. Velocity change all over time taking for change. That's acceleration. So for those who are still following about what we have discussed under fundamental and derived unit. Oh, I will have to clean the table so that I don't want to clean the graph so we can get the content of the graph. So as I was saying, along OA, velocity increase with what? With equal amount in each second interval for the first 6 seconds. Now, the uniform acceleration along OA is given. Uniform acceleration along OA. Uniform acceleration along OA is given as velocity change. Velocity change all over time taking for change. All over time taking for change. So we are talking about along OA now. So along OA, we have called this place, we have termed this place OA. So along OA, so the velocity increases with equal amount in each second interval for the first 6 seconds. For the first 6 seconds, it increases with equal interval. When we look into the velocity change in the graph, the velocity change in the graph for the first 6 seconds and the time taken for change for the first 6 seconds. For the first, the velocity change for the first 6 seconds can be found here. That is AP. That will be AP. the velocity change AP for the first time taken for change. The time taken for change. We want to get the time taken for change that can be found in the OP. Time taken for change, that is OP. So velocity change is AAP. So, and the time taken for change, that is OP. So that is AP all over OP. So we are dealing with velocity time graph. So, and I'm trying to say that along OA, so the velocity increases with equal amount in each second interval for the first 6 seconds. So the uniform acceleration along OA is given by velocity change all over time taken for change. That is AP. That is velocity change AP all over time taken for change. The time taken for change can be denoted here, which is what? OP. So the time taken for change before it changes again. So it takes this sign. But from here to this place, so that is the velocity change. That is AP all over OP. Now, acceleration gradient of the line will be equal to the velocity change is well, the velocity change here is 15 meters per second. This is equal to 15 meters per second all over OP. That is time taking. So time taking for change. And the time taking for change is, if you look before it change, the time taking for change is 6 seconds. So 50 meters per second all over 6 seconds. So time taking for change, that is 6 seconds. Before the velocity change, it takes 6 seconds. Now, 50 meters per second all over 6 seconds. And this will give us, if we 6 here, 1, 6 here, that will be 2.5 meters per what? We are finding the acceleration, 2.5 meters per second. So that is the uniform acceleration along OA, 2.5 meters. Uniform acceleration along OA. So the uniform acceleration along OA is 2.5 meters per second square. So that is uniform acceleration along OA. So with this now, we've tried to look into some little example about the velocity time graph. So how it looks like. Now let's look into the acceleration. So let's continue. Now let me try to explain something more about this graph. Now, if you look along AB, between the time interval 6 and 8, along AB, between the time interval 6 and 8 seconds. So the velocity does not change. So here now the velocity does not change. So the velocity may stay constant. So acceleration during this period is 0. When the velocity maintains constant, so the acceleration is 0. So from here down here now, so the velocity does not change, which means that the acceleration during this period is 0. And the gradient of AB, will be equal to 0. The gradient of AB will be equal to 0. So the gradient of AB will be equal to 0. Now, if you look into along BCD, so you will see that the velocity of the object is decreasing with time. Now, the velocity of the object is decreasing with time. If you observe the velocity along BCD, you see that the velocity of time or of the object is decreasing with time. So here now we have a retardation or deceleration. It is a uniform retardation. So here now, that is what we call deceleration or retardation. So the velocity of the object is decreasing with time. So we have a retardation or deceleration. So it is a uniform retardation. So I'm trying to explain more about the graph. Now, so retardation here now is the gradient along BD. The retardation of the object here now is the gradient along BD. So that is the retardation, and which is equal to, we can say, which is equal to BQ all over QD. Let me illustrate it on the board so you can get to see. So what am I trying to say? I said along BCD. So you'll see that the velocity of the object is decreasing with time. The velocity of the object is decreasing with time. So we have a retardation or deceleration. That's what we call retardation or deceleration. So it is a uniform retardation. And when we talk about retardation is equal to gradient along the BD. Gradient along the BD. And here now, the retardation or deceleration, here now, according to the graph you have on the board, is equal to BQ, all over QD. All over QD. That is the retardation. That is the retardation. What we did before was the acceleration when the body starts from rest. So, but now we are talking about when the object is going to rest. So that is retardation. And we said that retardation, that is gradient along BD. The gradient along BD. And which is equal to BQ all over QD. So BD all over QD. Now the BQ now is 15 meters per second. BQ is 15 meters per second. That is 15 meters per second. That is BQ. Now, QD now is 4 seconds. QD is okay, based on QD is 2 seconds. So the QD is 2 seconds according to the graph, 2 seconds. Now, when we divide 2 by 15, so we have 7.5. We are dealing with retardation or deceleration, 7.5 meters per second square. 7.5 meters per second square. Now, on this velocity time graph now, we have tried to explain the acceleration and the deceleration of the graph. Acceleration when the body starts from the rest, and deceleration when the body tries to go to rest. So that is the first example. Let us look into another example. Let us look into another example here. Let's look into another example. Because of the question, I may just try to be giving the illustration as graph immediately. So let me try to draw the graph out immediately. Then I'll be detecting the question then along. So we'll be putting it. Let's say that this is the velocity, meter per second. So meter per second. Now this place is our time, G second. Now let's listen to the question now. A car starting from rest accelerates uniformly and attain a speed of 80 meters per second. So the car started from rest here now. So accelerate from rest, accelerate uniformly and attain a speed of 80 meters. Now 80 meters. Let's try to get the velocity now. Our velocity 20 here, 40 here, 60 here, 80. Let us add one more to make it 100. So that's velocity. Now, a car started from rest, accelerates uniformly and attain a speed of 80 meters per second in 30 seconds. It accelerates in 30 seconds. So let's try to put our time here. 10, 20, 30, 40, 50, 60, 70, 80. Let me try to do some adjustment because of the question. Because of the question. Okay. 0, 10, 20, 30, 40, 50, 60, 70, 80, 90, 100. Now, let's listen to the question again. A car starting from rest accelerates uniformly and attain a speed of 80 meters per second. Uniformly attain a speed of 80 meters per second in 30 seconds. 80 meters per second. This is 80. This is our velocity in 30 seconds. So somewhere here, we look into it. Are you with me now? So in 30 seconds, it maintains this steady speed for another 30 seconds. It maintains this steady speed for another 30 seconds. It means that when the body reaches 80 meters per second, it maintains the speed for another 30 seconds. And we don't look at another 30 seconds here now. This 10 seconds, 20 seconds, 30 seconds. So under 60, I maintain for another 30 seconds. So that is 60. Now, I hope you are following. So you are doing it. Now, for another 30 seconds, it then slows down uniformly until it comes to rest in the next 40 seconds. It then slows down uniformly until it comes to rest in the next 40 seconds. It then slows down uniformly until you do what? Until it comes to rest in the next 40 seconds. What we are going to get is in the next 40 seconds, this 10 seconds, 20 seconds, 30 seconds, 40 seconds. This rest until it comes to rest in the next 40 seconds. So this is where the body starts from. Now, in the next 1 second, sketch the question not a sketch the velocity time graph for the motion of this car. That we should sketch the velocity time graph for the motion of this car. Now, so this is where it begins, and this is how it comes to rest. Now we can label the graph. Now we can call this place A, B. Yeah.
Any second from now.
As you round off, the time is about to over.